Okay, so the next speaker is Bluer. Huh? Do you have your first slide?
Okay.
Yes. So this is program has an error here. This says Mick instead of giving a talk, but Paul Endresen is actually the speaker for this presentation.
Hello,
so.
I'm Paul Endresen. I'm the CTO of Bluer. I've been in this industry for about 18 years now, and I worked mostly with high-performance computing and how we could make high-performance computing interactive. So I first deep dived into deep learning about 2 years ago, and to me it was really magic before that. After we deep dived into it, we saw that deep learning has very many parallels with HPC computing. And we saw that many things we did could actually be applied to deep learning. So let's see, there. So let's see. So this talk will be about interactive deep learning. What that is, how do we achieve it, and how does that apply to, for example, from R&D by the data scientist to actually deployment and use from day to day. So deep learning today is applied everywhere around us. So I will focus on how it is applied in our industry, especially in the seismic interpretation space, where the single data sets are the biggest and most challenging. That said, we believe the interactive deep learning approach applies to almost anything, as it solves some really fundamental changes. So, but first, let's take a step back, since this is a HPC conference. So deep learning today wouldn't be possible without the high-performance computing that we have on TPUs and DPUs. And there are very many similarities between HPC and deep learning. So let's first look at what I think that HPC, many people associate HPC with batch processing. So hands up for those who think the same, that HPC is batch processing. Okay, so let's first look at a traditional HPC workflow. So what we have here, we first have pre-processing of the data. We maybe have to copy it out to different nodes or copy it from cloud stores down to compute nodes. Then we have to run the job, and in the end, we QC the result. So if you look at a deep learning workflow, that would be pretty similar, except now that you have the data scientist in the picture, and how he creates his network actually dictates how the data has to be spread out to the different nodes to do the deep learning. So how many data scientists here? Okay, quite a few. So one of the things you have to do with deep learning is that you have to pre-process and chunk up and cut up the data and even maybe randomize the data. So why do we have to do that? That's because we need an even distribution of the data. Otherwise, the result will be bad or biased. When you label data, you have to make an even distribution. If you, for example, have 50 cats and 50 dogs, that you want to learn the network what is a cat and a dog, you cannot give it first 50 cats and then 50 dogs. So there is a partition problem on the data that you have to do first. So data preparation is a big key to success in the deep learning space. In my experience, the time it takes to pre-process this data is often longer than it takes to actually run the training. It's a big data problem. So there's hopefully something we can do about that. So let's look at the deep learning inference step, which is much more trivial. So what we see here is that we only have to put the data into the nodes and run inference, and you get the result. So let's say that we have a network that finds salt that you're trained, and now we want to run inference on that data set. So what do we get? We get the result that now has to be QC'd and controlled by the geoscientist. So are there many geoscientists here? Few? Okay. So he or she has to go through and QC and verify these results. Let's see. And check if it's correct. And today, we often see that they have to fix up these results manually. we actually have seen that it takes more time to QC and fix up the results of inference results from deep learning than it would have taken to actually do the workflow manually with a modern workflow. For example, interpreting faults or salt. So the question is, are we too optimistic about the promise of deep learning at this stage? So I would like to look at a different industry that uses deep learning heavily. And that is the automotive industry. We have today something called the SAE, Society of Automotive Engineers. They have defined a scale from 0 to 5. Today we are at level 2 in the automotive industry. That is where the car can drive on really nice roads, but might require human interaction. And for me, that is very similar to if you have really clean data, you can do deep learning on it and finds faults automatically. But it seems to me that much of what we do today is approaching level 5 directly and not putting the geoscientist in the picture at all. So let's go back to our confused geoscientist. See there. Where does he fit in the picture today? He or she can be part of designing the network and find out how that works. He can also be part of the QC and fix up after, but what happens in between in the deep learning space is it's really a black box for him. So what do the geoscientists feel about this whole process? I know some of them, and I think they're pretty unhappy. So what can we do about all this? There are 3 keywords. It's random access, compression, and interactivity. So first, we can solve the problem with how we actually pre-process the data. We can take it all away. So what we do, instead of baking the data up front onto nodes and so on, we actually use a random access adaptive compressed format that can stream the data directly into the deep learning network as it runs on the fly. So we don't have to chunk up the data beforehand. So in simple terms, the deep learning network streams, for example, the data directly from S3 storage during training. Think Netflix, but with Python APIs, and you can query anything 3D, 4D, 5D, for example. So the streaming of data is faster than the network trains, and you can stream the random order you want from the data. So that removes the whole chopping up of data that data scientists have to do. So let's say we have solved this problem. That opens up for new possibilities. Now we also want to get rid of the QC and fix up step after. But we want the results to be foolproof, 100%, not something that need to be QC'd after we have run the learning. So let's say that we want to solve only a single problem, and the mission is not to create the mother of all networks that can solve anything, but actually just solve the data you're about to solve a problem for. So think level 2 of autonomous driving on that scale, where the human actually still have a role. So since we can skip the cumbersome data pre-processing step, we can now train the network based on the geoscientist's input and expertise real time and run inference interactively. So let's see what that actually looks like. So I asked one of our geoscientists to see what he could do with salt and fault interpretation in 30 seconds. So what we're going to show you now is a network that has not been trained, but it trains interactively as the user, the geoscientist, is labeling the data. And the machine will eventually take over. So here we see the geoscientist is just labeling data. In the background now, it's actually learning on the fly. It starts with a fresh network, and immediately the computer comes back and finishes for you. You go and reinforce what's right. It continues to learn, and eventually it will have picked up what the geoscientists have done. Now we can go to another place in this data set, to different slice. Let's see, there. And it applies it learning immediately. If it's wrong, you continue to correct it until it has do the right thing. So there's only one step, and that is the geoscientist labels some data and continue until it's correct. So let's see the next data set. So this is salt. It's a 12,000 square kilometer, quite large data set, 120 gigabyte. And he starts by, this is quite sloppy, by the way. You can see it's missing the tops there. The network, it's the same network as for the faults. There's no difference. It hasn't been trained at all. It's training right now while it's labeling and learning what the geoscientist does. And based on only that single salt body, it finds in 15 seconds the other salt parts up there. Move to different slice, it immediately shows the salt. It's pretty bad right here, but he only spent 30 seconds. You can do a cross line through the whole data and see how it applies there. So that's half a minute of work by the geoscientist. So what is actually happening here? So this is what's going on. We have the geoscientist labeling the data. It sent information from the application that labels data into AWS EC2 instances that runs a service. That service calls into a PyTorch and Jupyter Notebook that actually gets metadata about what it has to fetch based on where the geoscientist paints. So it fetches data on the fly from cloud storage into the deep learning network and trains on that real time. And it also runs inference on the data that the geoscientist is seeing, so you get feedback. And what's interesting is that this is, have you ever seen, is a foolproof approach where the geoscientist can just continue until he gets the correct result, and then he's done. When he browse through the data and see that the deep learning network does the right thing, he can just apply it to all the data and be done. So we will go to another video where this is applied. And a little bit disclaimer. The video is cut and edited a little. We actually label 8 lines instead of 2 as in the video to get to these results. The blue is the deep learning network continuously learning based on what the geoscientist does. This is also 12,000 square kilometer of seismic. And it just reinforces positively what's right and not what's wrong. That's our deep learning network, but any deep learning network can be applied to this framework. Yes, absolutely.
Perfect. I got it.
So now, actually, 8 lines was labeled out of 4,000. That's 0.2% of the data. 0.2% of the data had to be labeled to run inference on the whole survey. This was originally a 3 months interpretation by 2 geoscientists. That was done now in 3 hours. Okay. So value, I think it's quite obvious. Overall, it's reducing time to oil. It shortens the time of tedious manual work. It's getting better and more certain results. It's realistic to do now. You can spend more time on what's important. For me, this is very important. It accelerates research and development. We see our data scientists don't spending any time on data management anymore. They don't. If they want to change their networks to take different sizes of cubes, blocks, they just change the code in the Jupyter Notebook. That's it. And in deployment, no need to QC or fix up data after, because this process is a QC process as you use it. So I think that's also very good. So again, it's a foolproof concept. The downside is, of course, if you have a bad geoscientist, you don't get any better result than what he does. So, and last but not least, using the vast knowledge of the geoscientists we have today is really important, because they can use their expertise to teach the machine. So that is really putting the geoscientists back in control. All right. Thank you. Any questions?
Over here is a question.
Hi. So I'm not a geoscientist, so I'm more interested in the deep learning view of this. My question is related to your choice of framework. Why PyTorch?
We see that it's about 30–40% faster, actually in general, and it scales better on multi-GPU. And it's cleaner in the way that it supports all different versions of Python, different versions of Windows, different versions of Linux. It's less hassle, and it seems more mature to us. We have done this with TensorFlow as well. For us, internally we use PyTorch, but we have clients who use TensorFlow.
Can you make any comments on the bias that the original interpretation on that image that you showed us imprints onto the whole process?
What?
The bias that you have there is you already pick salt on an image that already have an original interpretation on the salt body and is being imaged after that interpretation. Bias.
I'm not sure.
Well, the seismic imaging workflow will be you start with nothing.
Yeah.
You have a sediment flow. You start picking that salt body from top to bottom.
Yeah, in an imaging workflow.
Yes.
Yes.
I guess you started that interpretation process with something that already has that workflow.
Yes, it's already done at that time, yes.
And there is a bias on it, because there was an interpreter that came and did that.
This one is a pretty simple to find on that study. But we have done more advanced things like channels and gas chimneys. Mm-hmm. And so we see that whatever really apply it to, and depend on the size of data, you can change the width of the network. And we see that it really, because the network is only for that data set. Mm-hmm. So it fits very well, very quickly, is what we're seeing.
Okay, there was one question in the back here. You can tap down.
Yeah.
Were there any challenges with processing in the field or close at the edge versus moving the data to the cloud and processing?
So can you repeat that question?
So were there any challenges with doing all the real-time processing at the edge, maybe in the data center, versus having to move the data to the cloud and processing, doing all the analysis in the cloud?
No, this can be done either on the edge or on a local laptop even, or in the cloud. So
because the demo you showed, right? I think the block diagram had the cloud infrastructure.
Yes, so this is what we are running it on now. But we also run it locally on a machine with single or dual GPUs. So it could run on a Snowball Edge or similar, or on any computer, really.
From your little break in Spain.
Yeah.